Section 10.4, solving trigonometric equations. By the time we're done with this, we want to be able to use the identities we've been working with to solve the equations. And the identities we've been working with are our sum and difference formulas for sine, cosine, and tangent, and our double angle formulas for sine, cosine, and tangent. And here they all are. So this is just a little review of the last three sections. And hopefully you guys have these things down. Remember, there's a little, not so much a song, but a little saying to help you kind of remember some of these things. For sine, summations and differences, just go sine, cosine, cosine, sine. And for cosine, summation and difference, it goes cosine, cosine, sine, sine. And remember that cosines, we think opposite value. So an alpha plus beta means in the other part of the equation, it becomes a subtraction sign. And in terms of tangent, you have tan plus tan, 1 tan tan is kind of a saying to help you remember what goes on with tangent alpha plus betas. And then we have our double angles. No real sayings to help there, just unless you come up with something on your own. There we are. So we're going to use these now and solve. Now I'm going to solve some equations involving these identities. Sometimes inequalities as well. So here we are. First one, solving this inequality. We want to see where the cosine 2x, which is a double angle cosine, minus a sine of x is greater than 0. And so having to go back and remember what we do with these inequalities. Remember that greater than 0 means we are looking for positive values. And we set up a sign chart. Here's our interval, going from 0 to 2 pi, so we're talking about radians right now. All right. So let's see what we get here. One of the things we recognize is double angle. So maybe we go and we change this so that I can work with an equation maybe through factoring, simplifying somehow. I can maybe become the same trig value. So can I make a cosine 2x somehow become a sine? And we can. We know that a cosine 2x, one of the double angle formulas for cosine is it's equivalent to 1 minus 2 sine squared x. That's what that cosine 2x would be. And then we still have the minus sine x for the second part of that expression, and greater than 0. So this is just what cosine 2x is written in a different form. Right now we have a quadratic. Move things around. And I like, again, thinking about my square terms to be positive. So if I I divided everything by a -1, I get a 2 sine squared x plus a sine x minus 1, and then I'm having to switch the direction of that inequality sign there. And then here I can look at this and see that this factors. So we have 2 sine of x and sine of x, and I want a positive 1 sine x, so I'm going to go plus 1 minus 1. And we'd be looking for the zeros here so that I can set up my sign chart. So that would mean that 2 sine of x is equal to 1 when I set the first parenthesis equal to 0 through 0 product property, and sine of x equal to -1 when I set the second parenthesis equal to 0 through 0 product property. And divide by a 2, sine of x equals a 1/2. And now we're ready to find out what is this x equal. So our x's, which are our zeros for this sign chart, are x equals radians. So what radian values give me a 1/2 for sine? Pi over 6 does. 5 pi over 6 does. And how about for a sine value of -1? That happens at 3 pi over 2. So those are my zeros. And then I'll just set up my sine chart. So here, let's go over here. And let's see, we've got pi over 6. And 5 pi over 6. And 3 pi over 2. And we're going between 0 and 2 pi. So, all right, we test our values. So if we remember this, we plug some values in between our zeros here. So I'm going to plug something in between 0 and pi over 6. Let's just pick a value, maybe a pi over 12. If I put a pi over 12 in there, or a 15 degree, we're thinking about degrees. And remember, if we're plugging back in, probably want to plug it back into the factored form that we have. So we'd be probably checking our values in one of those two locations, plugging in the x's. I'd always probably go into the factored form. It's just easier. Remember, I'm trying to produce some positive values. So when I put a 2 times the sine of, let's say, a pi over 12 minus a 1, I get a positive value. And the sine of pi over 12 plus 1 is another positive, 2 sine of pi over 12 minus 1 is a negative. And then the sine of pi over 12 plus a 1 is a positive. So I end up with a situation where I get a negative in between 0 and pi over 6. And we keep testing, so let's test something between pi over 6 and 5 pi over 6. How about pi over 4? Put a pi over 4 in there for my x's, and I end up with a positive value. And then how about something between 5 pi over 6 and 3 pi over 2? How about pi? All right, put a pi in there, and we get a situation that gives me a negative, and I'm sticking pi in for x. And I keep testing between 3 pi over 2 and 2 pi. Maybe we do 11 pi over 6. Just picking the value. If I tested that, I get a negative as well. So through my sine chart, picking values of x, we determine that our solution, so therefore, we would say, if we're doing interval notation, we are positive between pi over 6 and 5 pi over 6. Oh, we're not supposed to be positive. We switched. Don't forget that. We did switch this to become negative, so we're actually looking for negative values now. We rearranged our order when we divided by that -1 to get 2 sine squared as positive. So be careful there. So we're looking for all of our negative locations. All right, that happens in interval notation between 0, pi over 6. We don't want to be equal to 0, so I'm not going to include pi over 6. And then we'll union that with 5 pi over 6 to a 3 pi over 2. And again, because 3 pi over 2 is where I'm actually equal to 0, I can't include it. So I have to union once again 3 pi over 2 to 2 pi. And there's my solution, where all the values of this inequality satisfy. Had that said greater than or equal to 0, then we would have included pi over 6, we would have included 5 pi over 6, we would have included 3 pi over 2. All Sometimes it might be beneficial thinking graphically what's going on, as in this case here we have where do cosine of 2 theta and cosine of theta look the same. Remember that a cosine of 2 theta, this is our b value, going back to chapter 8.3, and the b value affects your period. Your period becomes 2 pi, or in this case, 360 degrees over b. So we have 360 over 2, which means my period is 180. So we're horizontally shrinking the graph, and that's what the red graph represents. The purple graph would be the cosine of theta that we have up there. Anyway, we see in here that I have a couple locations where I have the same values of y, where these graphs intersect. So I'm going to have 4 solutions for this one. And let's see what we get. So remember, when we're solving, we want to be careful about not losing roots. So remember, you possibly lose a root when you start dividing the same value over the equation, over the equal sign. Instead, think about making one side of the equation equal to a 0 and working out the problem that way. So that's what we're going to do. We're going to take our original problem and we're going to subtract cosine theta to the other side. And now we get this equal to 0, and that's good. Once again, we have a double angle cosine that we can rewrite, and I already have cosines as terms within this expression here on the left-hand side. So I'm going to keep this cosine double theta as a cosine expression by rewriting it as 2 cosine squared theta minus 1, which is what double angle cosine, one of the answers for double angle cosine is, minus cosine theta is equal to 1. And then now we're ready. We have a quadratic that we can factor here. 2 cosine squared theta minus cosine theta minus 1 equals 0. 2 cosine theta, cosine theta. We want a negative cosine, so we're going to have a negative 2 cosine. We're going to add 1 to it. Zero product property. 2 cosine of theta is equal to negative 1. Cosine of theta is equal to positive 1. Little work here still. Cosine of theta is equal to negative 1/2. So we're talking about quadrants 2 and 3. And that happens at 60-degree reference angle values. So we're talking degrees. And we're referring to 120 degrees and 240 degrees. And where does cosine equal 1? At 0 degrees, or 360. So those would be our solutions. And we can see those over here on the graph. That graph was graphed in radians. 120 is 2 pi over 3 radians, so just over 2. There's the 120 degree, there's the 240 degree, and we can see 0 and 360 up on the top there, the max values. All right. How about this? 2 sine squared x equals sine x, once again within the interval of 0 to 2 pi. And we could have graphed this to see what we get. We're going to do this one by moving the sign of x to the left-hand side. So we get 2 sine squared x minus sine of x is equal to 0. And here, with only these 2 terms, we could the 2 sine squared x is not one of our double angles or a sum difference. So why don't we pull out a sine x first, and then I'll have a 2 sine x minus a 1 equals 0. So we really don't have to worry about any of our sum difference formulas or our double angles for this one. This is just kind of going back to generic, good old chapter 7 days of solving. We're ready for zero product property here, so sine of x would equal 0, and 2 sine of x minus 1 equals 0. So sine of x equals 0 happens in 2 places. Sine is equal to 0 at 0 and at pi. And solving for sine of x here is adding the 1 and dividing by 2. We end up with 1/2, which is a pi over 6, and a 5 pi over 6. And there's our solution. Make sure you didn't miss one. There. All right. This last one, cosine 2x equals 1 minus sine x for 0 to 2 pi once again. Now here I do see a double angle cosine, so we're going to be able to rewrite this one. Because I see sine on the right-hand side, I would probably take this as a 1 minus 2 sine squared x. Is how I would rewrite cosine of 2x. That equals 1 minus sine of x. And then move everything. I'm going to just kick all my stuff over to the right so my sine squared becomes positive. But I have a 0 on this side. And I have 2 sine squared x minus the sine of x. And when I subtract the 1 from the left over to the right, I end up with nothing. And this problem looks to be the same thing as the one we just had. So just with a simple change with a different value on the left-hand side of the equation, I end up with the same type of problem we just finished. Where I'm going to get the same solutions that I ended up with here. All right, there we go.